astronomers, and I'm Jay running tech, and with us on the board is Liz and Linda. Our president will not be joining us this evening. She had prior engagement, but she asked that I do announcements, and there are few announcements. Next month's members only star party on Mount Tam is Saturday, November 6th. And as usual, we ask members arrive at least 30 minutes before sunset. And I've looked that up. That would be sunset is 6:05 p.m. Pacific Daylight. So we're asking that you show up around 5:30. We also have in the works the next Observing Basics with our Vice President Bill Kircher, probably early November, but that's still to be determined. And those are the announcements, and I'll hand it over to Linda.
Okay, very good. I'm going to give.
I just thought we'd see if people could mute everybody.
I'm muting everybody right now.
Super. But me, right?
Yes, except you. Yeah, sorry.
Great. Okay, I always announce the next two upcoming meetings, so you can anticipate them. On November 17th, Dr. Gabor Basri, Emeritus Professor, UC Berkeley, who's spoken to us in the past. His topic is A Star is Born and Planets Too. We will learn how newborn stars prepare for the birth of planets. We live in a privileged time when we can see this development. This presentation is richly illustrated with images from major observatories on Earth and also in space. These have enabled us, along with computer modeling, to learn how stars and planets are born, and we will be able to watch the whole process unfolding at our November 17th lecture. We always meet on the third Wednesday. December 15th, not so fast supernova, highest energy cosmic rays detected in star clusters. Dr. Qi Fang, Assistant Professor, Department of Physics, University of Wisconsin at Madison. She will be speaking on the topic of cosmic rays and star clusters. It's not just light that we receive from the universe. Earth also receives cosmic particles that travel enormous distances and incredibly high speeds. Where do they come from? Is there a smoking gun? You will learn about these energetic messengers and what they say about nature's accelerators, including star clusters. So they sound fascinating to hear a talk about star clusters. Tonight's fascinating topic, living with a star, the sun, space weather, and our place in the stellar neighborhood. Dr. Phyllis Whittlesey is an experimental research scientist at the University of California, Berkeley Space Sciences Lab. She's leading the instrumentation on two of NASA's Heliophysics Division's mission in development, Escapade, which has been in the news recently, a dual spacecraft mission to study space weather at Mars, and Hermes, a space weather platform for Lunar Gateway, a space station planned for the moon. Dr. Whittlesey is also the instrument lead for a plasma instrument that's on board NASA's premier mission to the sun, the Parker Solar Probe. This launched in 2018 and continues to break solar proximity records every 3 to 4 months. We welcome Dr. Whittlesey as she discusses her research in space weather. We're so pleased to have you with us tonight.
Thank you so much, Linda. I really appreciate it. And what a wonderful introduction. So I'll just jump right into it. Gosh, this is so fun getting to hang out with all of you guys. I was talking a little bit earlier about some of my background, and I actually used to teach astronomy labs when I was an undergraduate. But before that, I was just a little enthusiast that really was fascinated with the stars, and I got my start in astronomy groups. So it's fully appropriate that I'm now giving a talk to you guys. I'm really excited. And by the way, you guys have like some very impressive speakers. I fear almost that I'm going to be talking beneath you whenever I'm giving this presentation, because it's very like space weather 101 and why it's interesting. My background, just jumping right into it. How do I proceed here? Every time I start up Zoom, it's a new thing. Yeah, so here's my background. This is me in the past on the left and me just a year or two ago on the right. Essentially, I've always been fascinated with space from when I was, at space camp on the right, and then on the left is, or sorry, on the left. And then on the right is one of my favorite pictures of all time. It was one of the few times that I was still enough in a clean room to have my picture taken next to the Parker Solar Probe spacecraft. This is down in Florida before our launch. A lot of things happened in between these two pictures. Namely, I got given a 4.5-inch reflector on an equatorial mount, which is a really silly mount for a really tiny telescope. And of course, I never figured it out because the mount was too heavy, the scope was too light. I lived in the city, what do you do? I wound up teaching astronomy for non-science majors. We got much better telescopes. We used compound telescopes for that, 10 and 12 inchers. I worked at a planetarium. So earlier people were talking about these star projectors. Those things are so cool, like the cast iron and the lenses. And actually I have to say, even though a lot of those, I don't even know if there's anyone that continues to make those, but there's definitely like I think a jealousy from planetarium people that don't have one of those and they have to get away with these digital things, but I digress. And then I broke a bunch of expensive equipment in graduate school before they allowed me to get anywhere near these beautiful spacecraft. So that's my brief background. But I figured that we could talk a little bit about solar physics. And I always think it's interesting to see how far we've come. So what I have is a picture not by me. This is a painting inspired by the 1571 eclipse. This is called Dionysius, the Areopagite converting the pagan philosophers. And so this is supposed to take place in the, oh gosh, I don't know, hundreds of years AD, I suppose. And basically this is just to show that like historically, like the sun and its omens have had a lot of interest placed behind them. And in fact, solar eclipses used to be feared, but in fact, by many modern scientists, and probably many of us in this room as well, given this is the astronomy organization, have always eagerly looked forward to solar eclipses in modern times, because it's one of the few opportunities that we get to observe the solar corona, which you guys will probably all know is the solar atmosphere. Which is in fact millions of degrees hotter than the surface of the sun. This is like an enduring mystery that one of the projects that I work on is trying to figure out why the atmosphere of the sun is so much hotter than the surface. It doesn't make sense. You'd think that the farther away you get from something hot, the cooler it would get. But in fact, that's not the case. And so there's a mystery to be solved in this phenomenon. And in fact, for people like me, there's a lot of work to be done to just try and understand what exactly is happening with these the atmospheric disturbances of the sun, right? It's in fact this dynamic magnetic structure that we can really only image whenever you blot out the surface of the sun, because of course the surface of the sun is so much brighter than its atmosphere. The atmosphere we really only see by phenomenon of light scattering off of electrons, in fact, a particular type of scattering in physics. And these two pictures that I'm showing you guys, actually, the picture on the right is an image of a recent solar eclipse. I don't remember which one. I think it's the 2017 eclipse. Is a big one that a lot of people paid attention to. I have to admit at this point, I haven't seen a solar eclipse myself in person because I'm usually too busy working, but one of these days it's going to happen. The picture on the left is actually a prediction of what, based on the physical understanding of what we know about the sun, we would expect the magnetic field to look like. So you have, can you guys see my mouse? I hope you can. You have all these long structures and these dynamic bright spots that are actually these long extensions of the sun's atmosphere. And actually these long extensions of our sun's atmosphere actually extend very, very long distances. But it's not just the surface of the sun that scientists like myself are interested in from the perspective of space weather. We're also interested, sorry, it's not just the atmosphere, but it's also the surface of the sun. So this is a video, and my experience with video over Zoom is very patchy. So I'm just going to continue to play it over and over again until hopefully enough frames come through. This is a picture of our sun from taken an instrument called AIA, which is on a space mission called the SDO Observatory, so the Solar Dynamic Observatory. And what we're looking at is really like some lower parts of the photosphere. And what I want to emphasize is all of the interesting structure that we see. So you see these loops on the edges. There's this little bright spot down in the lower right, and then there's this explosion on the sun, and a really bright spot followed by an explosion. And you can see these like clumps of dust erupting out of it and then eventually crashing back into the sun where you see more light again. And this is a really great example of the type of magnetic impulsive events coming from our sun called coronal mass ejection, or something that you would expect with a giant explosion of mass coming off of our sun. They're usually accompanied by really bright emission. So often X-rays, but really broadband emission. So not necessarily just X-rays, but typically they're classified by how intense of an X-ray emission we have. And these impulsive events are actually extremely poorly understood. We know what they look like, but trying to predict when and how they occur is really the core of a lot of what our space weather prediction and science is based on. So that's a picture at 171 angstroms, by the way, which corresponds to somewhere between, it's extreme ultraviolet, so between sunburn, but not quite X-rays yet. We do know, however, that a lot of these solar flares and ejections are actually based off of, again, another video, so I'll continue to play it until it makes sense, are based around or very close to or correlated with sunspots. Sunspots are dark, cool sections on the surface of the sun, and they've been observed actually for a really long time. I was looking this up beforehand, and I was impressed to see that the earliest records of sunspots date back to Chinese astronomers or astrologers. I guess at the time they were very similar in function. Yeah, so this is a NASA heliophysics video that love their, oh, that's not at all what I wanted to do, excuse me. But let me just get back to this. There we go. All right, so now we're back on it again. But basically these sunspots will have been observed for a really long time. Like I said, Chinese astrologers back from like like 800 BC, for example. And we know that these sunspots are cool regions where there's like magnetic flux that gets bound and sort of buoys up to the surface of the sun. And we tend to see coronal mass ejections and solar flares around these spots. Not always, but usually. So there's quite a bit of science around trying to understand these sunspots. And in fact, you guys will know this because this is a group of astronomers. You can actually, there's actually have been examples of sunspots seen on other stars. The star Betelgeuse is actually, I think, the only one that they've seen this on for sure. There's a dimming of Betelgeuse. I know I'm always looking forward to potential, well, supernova of the star Betelgeuse, as sad as I would be to see that leave this nighttime sky. What an amazing supernova it would be. But actually there's been recent dimming in Betelgeuse that scientists think is actually a result of a giant sunspot covering most of the surface of that star. So I think that's a pretty interesting phenomenon that you have sunspots that are really large. The image at the left here is actually an image from today from SDO, Solar Dynamics Observatory, of where our current sunspot is. So right now, in terms of the solar cycle, we're picking up, there's not a ton of solar activity. We do have some, but just that one sunspot. And I looked up the likelihood of it creating a flare, and it's very low. So very boring day for the sun. But you can also take a much closer look at these sunspots, and they have very interesting structure. There's these dark regions in the center. There are these filaments on the outside. If I project my slide forward, we can actually watch a video of these looping over and over again. And a lot of this magnetic structure on the sun. So when we say magnetic structure on the sun, what we're saying is that there's really hot plasma on the sun that's actually magnetized. So by following the motion of this plasma, we can make inferences about what the magnetic fields on the surface of the sun actually look like. So this is all sort of part of the larger ecosystem, setting us up to take a look at a very interesting event, which is one of the first solar storms that were ever observed by humans. So we've been observing sunspots for thousands of years. You know, people have been counting sunspots reliably since the 1600s, really. But it wasn't until 1851, I think, there's a gentleman by the name of Carrington who happens to be taking a look at one of these sunspots. This is actually his drawing at the right. He found a very interesting cluster of sunspots. You can see he's got his map here, and he's got his north-south, and then following and processing sections of the sun. And while he was observing it, actually, he noticed an extremely bright light. And actually, that extremely bright light was simultaneously observed by another man named Hodgson. And so they observed the same bright light, and this is actually the first observation of a solar flare correlating with a sunspot. About a day, less than a day later, actually 17.6 hours later, that bright spot had actually ejected a coronal mass ejection, an example of which is in this video to the left. And so that coronal mass ejection actually happened to be one of the largest to hit Earth in what I'll say, air quotes, modern times. So if you think about what the world was like in 1851, obviously there are no cell phones. There's no computers, there's no internet, but what is there? There's telegraph machines. So from the Carrington event, there were telegraph operators that received electric shocks due to compression of the Earth's magnetic field by this giant explosion of plasma that came rushing towards our sun. Again, it took 17 hours to make a 93 million mile journey. So very fast bubble of plasma coming at us very quickly. There are also some telegraph operators that reported that they could disconnect their telegraph machine from their power supplies and continue to operate and send signals. So what is happening is that since the magnetic field of the Earth compresses, it induces currents in any wires that we have all over the surface of our Earth, and you actually get power generated without being hooked up to any power source. So this is becoming more and more interesting to people as we start to predict what the likelihood is that these events, this so-called Carrington event, this giant coronal mass ejection, how often do they occur? And actually the video on the left is video from Stereo A, which is a spacecraft very similar to SBO. The only difference being that it orbits along Earth's orbit, but a little bit ahead. So, not quite off, like maybe, I don't know, at this time, this is 2012, say 90 degrees ahead of the Earth in Earth's orbit from the sun. And what you can see is this outer blue video and this inner red image of the sun are two different cameras that have been pasted together. And that big bright white explosion and then this kind of like snowfield that appears, that's actually a massive coronal mass ejection hitting the spacecraft. And that snow that you see is actually energetic particles, energetic protons, sort of similar to the cosmic rays that your speaker in a couple weeks is going to talk about, or a couple months, but super energetic protons that actually impact the CCD in the camera, and they interfere and they create that snow. So that's important because all of that like cosmic radiation, solar energetic particles, those really energetic protons, are not necessarily great for people or for spacecraft. Luckily, Stereo A, after being impacted by this coronal mass ejection, it was fine. Spacecraft are designed to withstand these types of events. But if something like this were to hit the Earth, we wouldn't have to worry about those energetic particles. We would just need to think about, for example, all of those electrical currents that are running around. Yeah, and we might get a really great one of these. So, of course, the aurora are created when energetic particles coming from these types of events come along and they compress the Earth's magnetic field. And as those particles transverse Earth's magnetic field towards the poles preferentially, they impact, ionize different atmospheric gases, and then you get the aurora. So for comparison, I don't know about you guys, but I've never seen aurora in California. But during the Carrington event in 1851, the aurora were so bright over the Rocky Mountains that it woke up miners and they started making breakfast. Because they thought the day had begun. So there are also sites of the aurora seen down as far south as the Caribbean, Queensland, Australia. I don't know where Queensland, Australia is relative to objects the same way I do in North America, but very bright indeed. So all because of a giant coronal mass ejection. So if something like that were to hit the Earth, even though it might send all of our electrical systems haywire, it would sure be beautiful to look at. So this is just a nice little cartoon of the way this whole system works, because I showed a lot of pictures, but we don't really have any diagrams. So I have very few diagrams in these slides. I much prefer to show images. But so essentially what you have happen is you have the sun over here to the left. This is not to scale, by the way. Don't need to say that, I don't think, but not to scale. You have the sun over here to the left, and basically the sun's extremely magnetized, shown by these red lines around the sun. It has a roughly dipolar field. That dipolar field actually changes over a 11-year cycle or a 22-year cycle, depending on how you count. And that magnetic field gets wound up over time, and it can buoy up to the sun's surface, creating these sunspots that you see over here. And then those sunspots have the ability to wind magnetic field even more, creating giant explosions that are energetic. They come hurling towards the Earth. Here's the Earth over here to the upper right, and compressing our magnetic field. So these coronal mass ejections and the solar wind in general travel at these supersonic speeds, and coronal mass ejections even more so than the supersonic speeds that the solar wind normally flows at. So it compresses Earth's magnetic field, and then when you have a really big coronal mass ejection, it just really squeezes the crud out of the Earth's magnetic field and creates currents all over the place, and then you get the aurora. So that's our real world application. So how do we learn to predict these coronal mass ejection events? Because if you think about it, in our current society that we have, having wild currents all over the place may not be a great idea, considering that we're much more electrified, I should say, than we were in 1851. Also, another important thing to consider is one of the projects that I'm on is this Lunar Gateway, the space station that's going to orbit the moon. And at the moon, that space station isn't within our own Earth's magnetic field. So not only do we have to worry then about currents or unwanted electrical effects like that, but you also have to think about these energetic particles, which are actually performatively like a type of radiation that isn't really very good for astronaut health. But predicting these things would be able to come up with ways for working around them. But I like to think of it this way. What are the top 3 reasons to send a robot to the sun? At my heart, I'm an experimentalist, and I like to do science with wrenches. So we want to learn more about how to live with our star. But first and foremost, I think all of the people in this group are going to share this sentiment, I hope, and that there's this desire for exploring what's out there. The first time you look behind a telescope and you see Saturn and you go, what is that? It's so beautiful. You feel something deep inside of you. And I think that that's a really important thing to consider whenever you're thinking about humanity. There's also this practical matter, like I've been discussing this whole time, of living with a star. How do you live with this dynamic, explosive ball of plasma in the center of our solar system, especially as, like we were talking before the break, as commercial space opens up and more people decide to explore our solar system, it's something that within the protective magnetic bubble of the Earth, we don't really have to consider. But as we move forward, we certainly will have to. And then there's always good scientific curiosity. All sorts of wonderful things come out of learning about our natural world around us. There are some people actually that think that by studying the sun, we'll be able to understand some of the complicated phenomena around processes related to nuclear fusion. So you never know whenever you wind up finding something out that winds up being serendipitous. So now that I've convinced everyone what the excellent reasons are that we should send a robot to the sun, I'll say we did, and I did as part of a giant team of people. We built this spacecraft called the Parker Solar Probe, named after a gentleman named Eugene Parker, who actually did a bunch of science related to these coronal mass ejections. It launched in 2018, and this is like really just but if you ever talk to a solar scientist, this is the most exciting thing that's happened in our field in 60 years, in fact, because actually this project's been in the works for 60 years. The whole mission concept behind this is, let's see if we can fly a robotic spacecraft as close to the sun as possible and try to model and figure out like what causes these explosions from the sun. Why is the solar wind supersonic, and why do the coronal mass ejections travel so fast away from our sun? Why is the solar corona millions of degrees hot, but the surface of the sun is only 5,000 degrees. You know, scientists don't like it when they don't have the answer to a question. So of course, let's go check it out. Another way that I think about this is, as astronomers, most of what are tools available to us are mediated through the use of light, through just photons. But it isn't until you get to actually build something and send it somewhere that you can use your other senses. You can not just look at things anymore, but you can count particles, and you can measure electrical fields or magnetic fields or currents, or you can take pictures from closer up. That's always a good option. I was just looking at pictures of Mars the other day from like pre-Viking and pre-Hubble, and then you look at it afterwards, and it's much better to take pictures up close. So that's what we did. And this is a really remarkable mission. I have this orbit plot to the upper right. Basically, we launched from Earth in 2018, and we slowly lower our perihelion, that is our closest solar point, from 35 solar radii to less than 10 solar radii. Actually less than 9 from the sun's surface. And the reason that this mission was so hard for us to build and has been a concept for 50 years is that it's really hard to go to the sun very close because it turns out it's hot. So half of our spacecraft is heat shield and radiator. You know, when you get to 10 solar radii from the center of the sun, the front of our spacecraft is 2,000 degrees, and we're traveling so fast that, you know, you can start counting our speed in terms of percentage of the speed of light. Well, decimal percentage of the speed of light, but still, it's very fast. So we use 7 Venus gravity assists to slowly lower our orbit down, which also means that we're also a planetary mission because we get to turn on our instruments as we fly by Venus. And it's a 7-year project. So this is a really spectacular mission that I had the privilege of working on as a graduate student and continue to work on currently. So what do we do when you go to the sun? Well, you might want to measure how hot it is. What else do you put on a spacecraft that goes to the sun? You might want to take pictures, like I said. You also might want to, and this is a surprising one, measure the wind speed, right? Because the sun actually emits this wind that's supersonic. So you want to figure out how quickly these CMEs pass over you, coronal mass ejections. You want to figure out how fast the wind is blowing, how quickly will what's happening on the sun reach the Earth, at least those things that aren't light. And then you might also want to measure the magnetic fields because there's so much about the surface of our sun that's magnetized, right? Our sun has this giant magnetic field that the entire solar system is encased within. So we want to see how that magnetic field changes over the life cycle of this project and over a brief duration of the sun's life that this mission will be orbiting about the sun for. So we put all those things together in different ways. We have several different ways of measuring wind speed. These are anemometers, by the way. I built this thing right there. Those 2 instruments are little proton and electron counters, I'll say, for low energy particles, not for energetic particles, but for low energy particles. We're really measuring the sort of soup of low energy ions and electrons that make up the bulk of the space between the planets and between us and the sun. We also have 2 little magnetometers that I put down here, and there's thermocouples and temperature gauges all over the spacecraft, except for, oddly enough, on the front of our heat shield, which is this big black thing in front. It's some sort of special carbon foam that they decided they couldn't put a thermocouple on because they were afraid the coefficient of thermal expansion might cause some damage or something like that. I don't know. I wasn't in the room for it, but there are temperature gauges all over the place. I should also say that when we're close to the sun, the front of the spacecraft is so hot that it glows orange. So that's a fun fact. All right. So here's a beautiful picture of our rocket launch. It's Delta IV Heavy. If there are any rocket nerds in the audience, watching the spacecraft take off was really terrifying because the Delta IV Heavy sets itself on fire before it launches, and I thought for sure it was going to blow up. So that was a pretty harrowing experience. Right. So it is currently on October 20th, and it's been about 3 years since we launched. There's been a lot of learning. We've had 9 of our orbits, 9 out of 25 so far. And we actually have our upcoming next solar encounter after our Venus gravity assist. So last Saturday, actually, yeah, it was Saturday, we had our Venus encounter number 5. These are really important for us to hit because if you don't execute the burns on these spacecraft appropriately, then you will not be able to continue throughout the mission because the spacecraft has about this much fuel. It's like a ball, like a beach ball size amount of propellant. And at the speeds the spacecraft is going, there would be absolutely no way that we would be able to get us back on track if we didn't absolutely hit those burns around Venus just appropriately. So I can report that our last Venus burn went great, and we're heading up for our next solar encounter at 12 solar radii. This is absolutely wild that we get this close to the sun. The funny thing about being close to the sun is that we pass through so quickly that it often takes us some time to try and disentangle what it is that we see. This graphic on this slide, I'm hoping that it's translating well. It's actually one of the first discoveries. It's an artist representation of one of the first discoveries from this mission, that we have streams of wind that are coming from the sun. They're not discrete like this. These are just sort of like flow lines or trace lines like you'd have in a wind tunnel, except that the wind that we see from the sun isn't explicitly visible, which is why we have magnetometers and other instruments to measure them. But there's some funny things that happen where you'll develop a little kink in the wind of the sun. And we're not entirely sure what this kink is, but we think that that particular special kink might have something to do with the heating of the corona and the acceleration of the solar wind. We're actually getting ready to, we're not getting ready, the sun is beginning to ramp up into solar maxima. We've had some interesting solar flares within the last year. So what's exciting about this project is that we still have several years to go, and we anticipate being able to uncover even more science as we get close to the sun and get to observe some of those coronal mass ejections in situ, where they actually get accelerated. So stay tuned for more interesting science from Parker Solar Probe. It's the bottom line. But we live in an entire solar system full of planets. And like I was saying earlier, the Earth is not the only place where humans would like to be. There's this whole interest in going elsewhere, namely the moon and also Mars. So there's another project that I happen to be working on that when I first wrote the abstract for this project, I couldn't really mention too much because it wasn't confirmed. And in the interim that I agreed to give this talk and now I'm here, it has been confirmed, so I can actually talk about it. So there's this special NASA mission called ESCAPADE. Yes, that's an acronym. No, I don't remember what it stands for, but I can guarantee it's very clever. It's a special class of mission that NASA's decided to start funding, which is essentially that it's designed to be low cost. And the thought is that now that we have so many opportunities as scientists, so many new rockets and ride shares and opportunities to put robotic projects in space, that we should try and maximize our ability to go everywhere. So this project, this ESCAPADE mission, right, fantastic acronym, is actually going to go to Mars, and they were going to build 2 identical spacecraft. They're quite small, each one's about 1 meter cubed. And we're going to send them to Mars together to study the way that the sun actually erodes the atmosphere of Mars. So not everyone on this call is going to know everything about Mars, so I went ahead and put it on here, is that Mars's atmospheric pressure at the surface is only about 2% that of Earth. So for anyone who's seen the movie The Martian, there's like that beginning part of the movie where there's this giant windstorm and it like knocks out the Martian base. Yeah, that's not ever going to happen because there's never enough gas on the surface of Mars to actually blow things over on the surface of Mars, even if the wind speed is really high. It's only about 2% of Earth. What's interesting about this is that precisely because there's not much atmosphere, but there is an atmosphere, if you look at, sort of wind back the time and you look at the way that atmosphere must have evolved, we can figure out that there must have been more atmosphere on Mars in the past. So there's much to be learned from Mars about how the sun can actually erode an atmosphere of a planet. Now, granted, Mars is very different from the Earth. One, it's about 1/3 the size of the Earth. I apologize again for one of the diagrams. Just let it wash over you briefly and I'll explain it in a minute, I promise. But the magnetic field of Mars is extremely different from the Earth. You almost can't compare it because Earth has a very strong dipole magnetic field generated by molten iron in the core through this magnetic dynamo. And it's what protects us from cosmic rays and energetic particles and all of those things that come from outside of the galaxy, and also from coronal mass ejections and these energetic particles that I was talking about earlier that we saw in the stereo footage, the snow. But Mars is smaller than the Earth. I don't remember exactly how much smaller. I know it's like a third or a fourth by mass, I believe. So considerably smaller, which means that people think, this is mostly theory, I think, that its core is probably not hot and molten anymore, which means that there's no possibility for the magnetic dynamo that we see. But what we do see from landers and other projects that have gone to Mars is that there's still this crustal magnetic field. So if you squint your eyes and look at that diagram really closely, you'll see that there's an image word in the center with two arrows pointing to these little loops on the surface of that planet. And those are crustal magnetic fields. What that implies is that at one point Mars's core was hot and it did have a magnetic field, but then it cooled down. And in regions where there's, say, especially strong piles of iron in the dirt, maybe there's some frozen in magnetic field. So this, we think, is actually one of the reasons that Mars has had its atmosphere eroded. And by retconning that and looking back at Earth, you can also say that one of the reasons perhaps that we've been able to hold on to our atmosphere here at Earth is precisely because we have such an excellent magnetic field. Venus, I couldn't tell you about. It's complicated. No one really understands how that works, I don't think. It's very, yeah, there are quite a few missions we'll talk about in a minute that are going to go to Venus to figure this out. But essentially what ESCAPADE is going to do is it's studying atmospheric change at Mars. The way that we plan to do that is actually by using two separate spacecraft together to figure out what's happening upwind of Mars and what's happening downwind of Mars, if you think about the wind as coming from the sun. So what we plan on doing, these are our goals for our project, but essentially, I think this is probably more of a nuts and bolts kind of crowd here. What we plan on doing is taking two spacecraft and having them orbit in two different paths at the beginning of our project. That way we can have something, say, an observation in one point and then come at it later and check it again with another spacecraft. And this is because the solar wind and the solar environment around Mars is going to be very dynamic because there's not a ton of magnetic field protecting Mars like we have on Earth. The payload is actually going to be very similar to Parker Solar Probes. You have a magnetometer, a couple detectors, things to measure electric fields. And then we have a camera, but it's really only a star tracker. So it's not really a camera, but we do have plans to try to take selfies of the spacecraft from each other's star tracker cameras. So that should be fun. Here we go. I have some orbit plots from this project. The way it happens is basically we're actually shopping for a rocket. So we don't have a rocket yet. This is a weird function of the way that this type of NASA project works. Originally, we were going to be a ride share with our, say, prime mission, which is a mission called Psyche, which is going to an asteroid. But for reasons that we don't need to go into exactly, NASA decided to pull us from that spacecraft. It actually had to do with how quickly we were going to fly by Mars on that rocket. And now they're looking for us for another rocket. So what's cool about this project is that we can actually launch from Earth and hang out in low Earth orbit for a long duration of time. And then whenever we decide we're in the right location to be to head off to Mars, we slowly raise our orbit over time, and then we head off to Mars. So it's kind of this cool waiting that we get to do in low Earth orbit where we get to do all of our checkouts. This picture over on the right, by the way, this is actually from a SpaceX rocket. They have a bunch of Starlinks down here on the bottom, and then this tube up top is a rideshare configuration where they have a bunch of different scientific satellites all clustered around the outside, like, I don't know, like Brussels sprouts, like Brussels sprouts to a stalk, kind of what it reminds me of. But this is a bit of an interesting convention, I think, that we're going to see more of as we proceed farther into the era of commercial space. Lastly, I'm getting close to the end here. So I tried to leave a lot of time for questions because I love fielding questions. I talked about Venus briefly earlier. Venus is another weird oddball whenever you come to living in the solar system, and that Venus has a thick atmosphere. It actually has an extremely thick atmosphere and a very corrosive atmosphere. I think the record for a lander surviving and transmitting data on the surface of Venus is less than 30 minutes. It's probably one of the Russian ones back from Russia when Russia was the Soviet Union. But there's a lot of interest in Venus because Venus in a lot of ways looks a lot like Earth's twin. The only difference, so they have about the same mass, right? Venus is about 98% of Earth's mass. And, you know, Venus is a little bit closer to the sun, but that doesn't explain why it's so hot. My dog wanted to say hello. But Venus doesn't have a magnetic field. It has an induced magnetic field, much like Mars does, that doesn't really explain why it has so much atmosphere. So that's a question that is left to be answered, and it'll probably be answered by a couple of these projects that were just recently selected. So there's this project called Veritas, I think that's coming from JPL, that's going to be scanning the surface. And then this other project called Da Vinci, it looks like they're going to have some type of lander component to that mission. So it should be very exciting. With that, this is actually my last slide. So what I would like to convey is that our place in the solar system and all of the planets are actually wholly dictated by our interface with the sun and the wind coming from the sun that's standard and sort of ubiquitous. But then from time to time, we can have these impulsive events that we really take for granted here on Earth because we have our own magnetic field that protects us so much. So as we enter into this new era of space exploration, I think that there'll be much more conversation about how we interact with the dynamic supersonic wind that blows from the sun all the time, especially as we go to places like Mars and Venus and elsewhere to try and set our foot on other planets. So thank you. I guess, I don't know how questions work, but I see a bunch of questions in the chat. Should I be looking in the chat for questions?
I've been noting there's been one question and some chatter. But thanks.
Excellent.
Thank you. First of all, thank you for the presentation. Very fun stuff.
Yeah, you bet.
So we had one question from I don't know if it's I want to say Kayla, but it might be Kala. Question for our speaker. Given that the sun is in solar maximum, is it normal that it would have only one sunspot for a while in a day? That seems very quiet. Is this maximum cycle average more or less intense in activity?
Yeah, that's a great question. There's a whole subsection of science just dedicated to trying to predict the solar cycle in advance. I debated on putting a couple slides in here talking about the solar cycle and ultimately decided against it. But it is interesting. I think that there's still quite a lot we don't understand about the sun's cycle. This is actually the type of stuff that keeps me up at night. And maybe that doesn't matter to you or not, but it is interesting to me because if you think about the sun's cycle, it's this 11-year cycle, but it's actually a 22-year cycle because what happens is you have the sun's magnetic field and it's coming out of the poles and going down into what we think of as south. And then it gets complicated and then it switches and it comes out of the south and it goes into the north. And so, you know, this flipping happens every 11 years. But if you think about flipping this way to this way to this way back again, that's actually a 22-year cycle. So if you think about how long we've been observing the sun's solar cycles, you know, as a species, I think of it pretty much, if you count like a reliable solar counting, it's been since the 1600s. You know, that's a really short period of time over the sun's 4 billion year life so far. So is it normal? I don't know. There have been periods that we've had before that are more like minimums. Like there was the Maunder minimum, which I think was in the late 1600s. There was an interval where there were basically no sunspots at all during solar maximum. But we'll find out. I think that since we're still ramping up into solar maximum, there's still time for a lot of sunspots. And in fact, a couple weeks ago, there were some nice looking sunspots I was checking that out myself. But certainly compared to solar minimum, there were almost no sunspots during this last solar minimum. It was really disheartening because I was giving a talk and there was like nothing. It was blank. I had nothing to draw on. So I hope that answered your question.
Thank you very much. We've had another question appear, and also feel free to, if others have questions, type them into the chat, or if you want to click the button to raise your hand, or if you just want to try to unmute yourself and speak up, that's fine too. This question comes from Ken. Ken asks, can you please clarify why the sun's corona is so asymmetrical? Is it due to CMEs or magnetism or other?
Yeah, that's a great question. So can I clarify why the sun's corona is asymmetrical? It is very asymmetrical depending on what period in the solar cycle we're looking at it. Essentially, there's this funny phenomenon, and it's not also, again, I'm going to give a scientist answer, it's not fully understood, but what we can see is that as the sun's magnetic field begins to flip, it gets very complicated. Couple that with this other phenomenon where the sun is not rigid. It's actually this ball of plasma, right? No, I mean, yeah, of course it is, but it actually rotates faster about the center. So what we see is that as the sun rotates faster about the center than the poles, you get this kind of winding effect that happens on the sun, where you get all that magnetism gets dragged around, and really it is like winding up a, I don't know, like a piece of wire or something until you get to the breaking point. When you get that breaking point, you get really complex magnetism, and it takes quite some time for all of that winding to occur. So it's because of this differential rotation, and then also some special thing happening in the core of the sun that we don't fully understand, that leads to asymmetrical magnetism. So is it due to CMEs or magnetism or other? I would say it's due to magnetism coming from rotation, coming from the dynamo. And on a smaller scale, CMEs are a result of that complicated magnetism.
Thank you. Next question comes from Steve. For Parker spacecraft control, how does NASA compensate for all the EM radio interference?
Yeah, that's a great question. So NASA's gotten really great at picking out the specific frequency for our spacecraft. I should also add a caveat. I'm not a radio person. I have an amateur radio license, but I don't own a radio. So I'll tell you what I know, and hopefully that will work. Basically, we have a couple single frequencies that we use, and there's specific types of protocols that are used for communicating with the spacecraft. In terms of all of the EM radio interference, I assume you mean close to the sun. And actually what's fun about the spacecraft is for a period of about 15 to 20 days around our closest solar approach, there's basically no communication with the spacecraft. It operates autonomously on its own for 15 to 20 days, which is actually horrifying because it has to point the sun, point the heat shield at the sun, correct for photon pressure. It's pressure from light rotating the spacecraft due to offsets in center of mass. It also has to run the reaction wheels to make sure it stays pointed, and then also desaturate them by autonomously firing thrusters, controlling the solar panels. It's really terrifying. But it's also when people tend to go on vacation because if something bad has happened, there's nothing we can do about it. So you just let it run on its own. We do get what we call beacon tone. So we'll get just a single tone that's unmodulated from time to time. And depending on what the frequency of that tone is, then we know what status the spacecraft is in, whether it's in like, you know, all systems are good, science instruments are running, to I'm not so great, you know, and it's based on that frequency. So it'll go silent, and then whenever it comes out of a solar encounter, we'll like downlink all the data after the fact. It's a great question.
All right, we have a question from Dan, and then I will call on the hand raised from Marianne afterward. Dan asks, hi, what is the latest thinking on why the temperature in the corona is so much higher than the surface of the sun? Thanks.
Yeah, that's a great question. That's actually one of the primary reasons we came up with the Parker Solar Probe project. We can tell by looking at spectroscopically at the corona that it's extremely hot. Again, like I said, millions of degrees hot, and that the surface of the sun, again, spectroscopically is only about 5,000 degrees. I don't know if that's Kelvin or Fahrenheit or Celsius, but at these temperatures, I don't think it matters so much anymore because it's hot. the thought behind it, it's multifold. It has to do with special types of electromagnetic and actually waves, electromagnetic waves from like motion on the surface of the sun shaking. I'm doing this with my hands thinking it's going to mean anything, but it probably doesn't mean anything. But basically we're thinking that sort of plucking these magnetic field lines at a specific frequency has a way that it resonates with ions or particles in the sun's atmosphere, and it enables the wave energy to get transferred onto the particles in form of temperature. The specific mechanism between how that happens is yet to be fully determined, and we know that there are multiple causes, but so far I've seen some research coming out of this project indicating that that might be the primary mechanism. Again, great question.
All right, thanks. I'll go to Marianne next, and afterward, Philippe. Marianne.
Okay, I was wondering, I guess the brightness of the aurora is related to events on the sun, is that correct?
Yeah.
Is there any way to predict that? Because I must admit, to a selfish motive, I would like to go somewhere sometime when the aurora is very bright, because I was told that you could see the colors of the aurora with your naked eye only when the aurora is very bright. Otherwise, you just see white light. The camera can see the colors, but you can't see it with your own eyes because your own eyes are not as sensitive to color. And so is there any way to predict when the aurora would be especially bright?
Yeah, great question. So is there a way to predict when the aurora are going to be bright enough to see, admittedly for selfish reasons, which I have to say, I also share those selfish reasons. I haven't seen the aurora in person myself. So this is actually,
I've been to several countries to see the aurora, and I only saw the white light with my naked eye. And
yeah,
it's kind of frustrating.
So I would say that your best chance of seeing the aurora intensely is whenever you have large coronal mass ejections that hit the Earth. There's sort of like a low level aurora that happens all the time. That's really hard to see with your naked eye, which is probably what you're referring to, that just comes from natural wind speed changes from the solar wind. That's like, it's just, again, solar wind is blowing at us all the time. It changes wind speed. The Earth's magnetic field is going to contract and shrink a little, and maybe it'll be particles and you get some aurora. But when the sun is at solar maximum, give it a couple of years, and then there's a couple strategies, I'd say. If you feel like a jet setting type, you could hop on a plane when you see a coronal mass ejection. It'll take you about a day and a half to get to the Earth under most circumstances. And maybe you could like run up to Canada and go take a look at it. What
is it that, I'm sorry, what is it that happens on the sun a day and a half before?
So no, you're asking the right question.
What should I look for on the sun? Or
actually, yeah, you know what? There's actually a website called, I think it's like, if you look up a website like called Space Weather, something like that, like Space Weather Monitor, something along those lines, it'll give you a probability of how likely there is to be a solar flare that would be on the sun. And there's probably also going to be news articles about coronal mass ejections that could hit the Earth, because when a coronal mass ejection hits the Earth, that's when it's going to be bright enough to see the aurora. But basically, it's really hard to predict when those happen. So when you first see one erupt on the surface of the sun, or a very special type of solar spot on the sun that looks like it's likely to create a coronal mass ejection, that's probably when you're going to have a high likelihood. But essentially, it boils down to look for a time when there's a lot of sunspots on the surface of the sun, and that's going to increase your likelihood of seeing strong aurora colors with your naked eye. But that won't happen for a couple years.
Oh, I'm not sure if I'll still be around because I'm getting very old.
I understand.
But thank you very much.
If I Google Space Weather Monitor, I see a spaceweatherlive.com and then several others from NOAA and NASA and ESA.
Yeah, so I think the one from NOAA is the one that I'm thinking of.
Next up in the queue, we have Philippe, and then it'll be Tom and Ken. So Philippe had a question typed in. What is the source of the sun's magnetic fields? Internal thermal convection currents, differences in rotational speeds across the surface or depth layers?
I have to say, I'm not an expert on the interior of the sun. I'm sort of like a top-up kind of person. So I think that I would actually be misleading you if I attempted to answer this question. My assumption is that it is probably something deeper down in the sun, closer to the core. But the tricky thing about making measurements inside of the sun is that it's a special field called helioseismology. You know, it's similar to Earth seismology, but we can't put seismometers on the surface of the sun. So they actually have to use a special type of image called a magnetogram, which uses I hate using this word in public, it uses a quantum mechanical effect that involves splitting of spectral lines. So they look at changes in those lines to try and do remote seismology on the sun. So it's still very much a difficult thing to do. There's actually a couple mission concepts that are in development to try and have satellites stationed around the sun just to do this type of work, to try to better understand what's inside the sun. Currently, I think there's a lot, we have some rudimentary measurements of what's inside of the sun. There's also been a lot of models that have been done based on the physics that we currently have. And so those two things are probably going to converge at some point in the future. That's my answer.
Thank you.
So
yes, go ahead.
before me, I saw Lou Epstein's hand raised. And Lou,
I was about to say someone's telling me Lou's wishing to speak. So let's
Lou,
hand it
you're
over
not-
to Lou.
Lou, take it away.
Yeah, can you hear me? Am I communicating? Okay,
You're
Yes,
great.
sir, go ahead.
I want to ask you a question that's kind of bothered me ever since I was a kid. When you get a bunch of solar material, the plasma, ejected from the sun, it's made out of particles that have radically different masses. The protons weigh a lot, and the electrons, they don't weigh much at all. And then you get a force on them, whatever the force is, radiation pressure, God knows what it is. But you would expect that the acceleration of the lighter particles would be a lot greater than the acceleration of the heavy particles, and the cloud would be torn apart. Except for the electrostatic attraction, the protons would go one way and the electrons would go the other way. What holds it together so that you can talk about it as one thing?
Yeah, that's, wow, a very deep question, I should say. You know, have you taught a plasma physics class before? Because you really seem like you know what you're talking about. I don't know if you know that you know what you're talking about, but you do. Gosh, how do I answer your question? So your question is, for coronal mass ejections, there's particles in them with different masses, namely the protons, and then the electrons, which are 3 orders of magnitude lighter in mass, right? But equal charge. So, okay, how do I answer this without going into a plasma physics lecture? I think there's 2 parts. One, when you look at the ambient, this is not a coronal mass ejection answer, but here's one part of the answer to set me up for the second part. When you look at the heliosphere and all of the space in between, it's very diffuse, but it's made up of primarily 2 things, right? Protons and electrons and some heavy ions. And then there's empty space and photons, of course. The protons and the heavy ions actually blow away from the sun continuously because they have heavier mass. The electrons, on the other hand, are much lighter, but they have similar energy and similar temperature. So you can think of the electrons as like this underlying soup of buzzing bees that actually bounce around all over the place and don't really pay much attention at all to the ions. The reasons for that have a lot to do with the fact that the ions really are heavier, and because they're heavier, they tend to respond much slower. So even though they're experiencing similar force, that requires more energy to move them quite so much. So there is that electrostatic attraction, but in this case, it's really like a differential velocity. Something that we do see from coronal mass ejection, so I'm teeing up for the second half of that question now. Something we do see from coronal mass ejections, because the particles from them tend to be so energetic, is that the electrons actually will zoom out ahead from the ions, and all of the ions tend to stay behind because, again, if you give two particles the same kick, but one is much heavier, it's not going to travel as far as the really light thing. It's going to go pinging off. And so that is something that we see from coronal mass ejections. And I think in order to answer your question any deeper, in all honesty, I really will have to start launching into plasma interactions, but it's a very perceptive question, Lou, I have to say, very good.
Well,
I hope that was a sufficient answer for the interim.
yeah, thank you. Thank you.
Yeah, you bet.
Thank you, Lou. Next in my queue is Tom with your hand up. Go ahead, please.
Oh, yeah. I really enjoyed your lecture and your presentation. It was not below anything. It was right on the mark. And I have a much simpler question. Lou's always dives much deeper than I do. But how many coronal mass ejections have occurred since the launch of this Parker mission? And so it's been about three years, I think. So how many have occurred? And the other part of it is, it seems pretty scary if you're going to be 3 million miles away from the sun and all of a sudden you get hit by a coronal mass ejection. So you're kind of taking a risk at losing the spacecraft altogether. So go ahead and address those two.
Right. Okay. So I'll see. What was I forgot your first question already, but I'm going to answer your second question first and then ask your first one again. So it is terrifying having a spacecraft be really far away from this, from where we can do anything with it, and then having it suddenly hit by a coronal mass ejection. The way that we deal with that is there's a lot of design and a lot of wringing of hands. And because there's a lot of wringing of hands, there's a lot of design and forethought about how to deal with that. Namely, there are a lot of redundant systems on spacecraft like this. So they'll often launch with with 2 copies of the same computer or 2 copies of the same board in a computer, and one will stay unpowered and then the other one will be powered on. And then if something bad happens to that, then you hope that there's some piece of software you've written somewhere in the BIOS equivalent of what a spacecraft is to be able to switch to the backup. And if not, then the computer's job is to just put the spacecraft in a safe mode where it's pointing in a direction and it's hauling along and everything's going to be fine. So there's multiple levels of safety, especially for a spacecraft like Parker Solar Probe. We have little sun sensors specifically designed just to keep the heat. I'm doing a dance. I'm doing an interpretive dance. We have sun sensors designed just to keep the heat shield pointed at the sun. So at its most basic level, if the spacecraft did get knocked out by a CME during, say, worst case scenario, during an encounter, we have some very rudimentary processes that would probably be able to keep it online. And if the CME that's so big that it knocks that out, then it's going to be absolutely historic. We're going to get some amazing data right up until the point where it cuts off, which will also be amazing. Your first question, I remember it now, was about how many CMEs have occurred since the launch of Solar Probe. The number of coronal mass ejections varies based on where we are in the solar cycle. It's less when we're at solar minimum, fewer sunspots, fewer coronal mass ejections, fewer flares. But as you ramp up, you get more. So we launched essentially in solar minimum, which is great, actually. It gives us plenty of time to understand what it is we're looking at without the added complexity of these explosions that we have to measure. I'm going to quote averages for you. So on average, during a solar minimum period, you get maybe 1 or 2 coronal mass ejections per week. So it's quite a few. And they're very small ones. So you can have big explosions or you can have little tiny puffs, something that doesn't really matter. But still technically counts because it's a little bubble that blows off the sun. During solar maximum, you can have several per day. And we see that sometimes. The other tricky thing about coronal mass ejections is they're also a little difficult to measure remotely from the Earth. So the way we do that is with, I had that blue video, it's like a coronagraph image from something like stereo or SVO. And those have a false ecliptic disk in the center that blots out the sun. And we can visually try to recognize when you see something like looks like this bubble shape coming off of the sun, and it goes outward. That's a way that we detect CMEs. But there's not really there are some people that are looking at like machine learning algorithms to do CME detection from those images, but it's still very much like I did my time as an undergraduate counting CMEs on a coronagraph. So that's the current estimate. We'll get better as time goes on.
Okay, next is Ken, and afterward will be Steve. These are both typed questions. Ken asks, does the spacecraft orbiting near the sun have magnetic parts? Is it hard to steer or predict the orbit of the craft in such strong, irregular magnetic fields?
All right, so does the spacecraft have magnetic parts? That's a fantastic question, because since the spacecraft has to measure magnetic fields, namely, we're trying to measure DC magnetic fields. There is an entire program created for a spacecraft like this, just to keep the entire spacecraft as unmagnetic as possible. The people that build the magnetometers that measure the magnetic fields absolutely loathe when a spacecraft is magnetic. And I think this is interesting because I also, as a instrument lead for a project, for an instrument that measures low energy electrons, which are also highly influenced by magnetic fields, I also loathe magnetic fields on a spacecraft because they warp particles, and then it becomes very difficult to see whether the particle's traveling this way because it was going that way already, or is it going this way because the magnetic field of the spacecraft bent it, and that's why it's bent. That is, yeah, so it's a great question. Actually, when you're assembling things on a spacecraft, like this, that has this magnetic, we call it magnetic cleanliness, which is kind of a funny term. But you actually, when you bring anything into the clean room where the spacecraft is being assembled, there's a requirement to measure the magnetic field of that object, whether that object is anything that's touching the spacecraft, especially screwdrivers, for sure, you have to measure the magnetic field of that screwdriver. And if it's too magnetic and there's a risk of making the spacecraft more magnetic because of it, you kick it out and you have to go degauss your screwdriver. For fear of waxing on forever, to answer your question, because it is one that I think about a lot as a person that's around spacecraft often, there's a fun test that we do towards the end of building the whole spacecraft, where we suspend the whole spacecraft from a crane in the ceiling. We actually swing it in front of other magnetometers to try to measure the magnetic field. It's very difficult to do, and we have to swing it like that because on Earth, we have a very strong magnetic field in the tens of thousands of nanoteslas. And on our spacecraft, we require magnetic fields far lower than that of the spacecraft itself. So I think that answers in part your second question, which is it hard to steer the craft in response to magnetic fields? And I think the answer to that is not too much. We're far more interested in things like photon pressure, which can be especially important for a spacecraft like ours with a big heat shield in front, and it's white. So you have this big white reflective thing in front. And when you get close to the sun, the photon pressure actually tends to matter because of the center of mass. You get things like rotation. At the beginning of the project, well, I think I've answered that enough. I hope that answers your question. It's much less about magnetic fields of the spacecraft and much more about other things like photon pressure and, like whatever small impulse you might get from the solar wind itself.
Okay, thank you. Next question comes from Steve. If a Carrington level CME hit the Earth, what might the damage be to our technology?
I feel almost guilty answering this question because it's often like what a scientist like myself will say in front of governing officials when we're trying to convince them that this is research that's valuable. But I'll go ahead and indulge a little bit. So one thing that we see with low-level CME events, so not something like Carrington event, is GPS. So GPS satellites or other sort of navigational satellites will occasionally get a energetic particle event from something like a coronal mass ejection that will cause it to fail. That's something that's probably critical. Getting closer to Earth, another thing that you see is transpolar flights, or flights that get close to the poles. For any like coronal mass ejection that you have, you get higher doses of radiation. Using my imagination and thinking about what a Carrington-like event would do to our technology, our power grid, I would say, is probably at severe risk, especially up near like the Canada-US border. There's a lot of ability for induced currents to blow things like transformers. There are actually whole groups of people now that just model what would happen if a coronal mass ejection like the Carrington event were to hit the Earth. And it became much more interesting for people like myself after we saw another Carrington level CME event hit stereo A, and that footage that I showed earlier from that spacecraft. Previously, I think a lot of people had thought, the Carrington event, it's, you know, it's like 1 in a million years. It's just so happened that we saw it at the right time. You know, what are the odds? And then another one happened like 100 years later, but it hit Earth, and it hit something near Earth. So certainly, you know, power grids, that's for sure going to be a problem. Satellites, GPS, that's also probably going to be a problem. It would be pretty, I think, well, interesting to see the results of something like that for sure. Lots of blown transformers, absolutely.
That's it for questions. I see Linda waving. Did you want to? You're on mute, Linda, so I don't know what you're saying.
Good. Got it. Okay. I remember a few years ago when the Northeast coast went blank, New York City was dark. Was that a Carrington event? Was that a Carrington event?
I'm not sure. What year was that?
I'm trying to remember.
I got a web browser here. I can find this out.
Because people in New York City were going out at night, looking up and wondering what all those things were in the sky that were bright and calling an emergency. And they were, of course, stars. And they hadn't seen them. But I have never heard of another event like that on the planet. Have there been other events where big parts of an urban area were suddenly thrust into the dark like that?
I heard of a similar thing, but it was not related to a CME. I heard something similar about like Los Angeles brownouts, like probably more than 10 years ago. Right. Similar event where like, you know, you have like some brownout that causes, you know, a lot of urban lights to go out. And then all of a sudden people look up and see a giant dusty thing and they go, what is that? I should call 911. And it's the Milky Way. I don't know if something like that was caused by a Carrington event. I haven't heard of it.
Was it assumed to be caused by a solar mass ejection, though, wasn't it? Didn't people know at that time that was what did it?
I wish I knew what year it was, because I'd be able to figure that out. Was it like 89, maybe? I don't know.
See, that was the year of the earthquake. I don't
remember. That was the year of the earthquake.
But I mean, I always thought, where next? When next? And if there's any way to know in advance, here it comes, get ready, shebang. You know, if something like that would hit, I know it has to be facing us correctly. It has to be facing our line. And,
yeah, that's right.
2003.
2003.
Interesting.
Yeah.
I was gonna. There appears also to be one in March of 1989.
You guys are making me feel like a very bad space weather scientist here for knowing these things, and I don't.
I never forgot how impressive it was.
I have a keyboard and several computers.
Fascinating. Yeah, so I mean, it is entirely possible, right? Like having chunks of these power grids go out because of blown transformers and currents running backwards along lines, or having power surges. It certainly wouldn't surprise me. Why New York specifically? I'm not really sure. It's a good question. I'm going to look into this.
Yeah, it took out, you know, a wide swath of area, and it wasn't just for, I think, overnight. I mean, it lasted for a bit.
Yeah, wow, fascinating. Well, gosh, I'm so delighted to learn something today. Thank you.
We have a new question from July in the chat. Any idea how a CME might affect our bodies or any life forms on Earth?
Yeah, great question. So on Earth, you're mostly fine, again, unless you're really bound to electricity, like we've been discovering here. Wow, I really need to do some research on that. That's fascinating. as far as life forms outside of Earth, it's mostly the energetic particles. So the energetic electrons and the energetic protons that you would see from something like a coronal mass ejection. That's the type of radiation that's a big concern for astronauts in particular going on like a Mars trip. I saw a statistic once. I don't want to quote the statistic necessarily, but on a 3-month trip to Mars, which is, like sort of average of what people are thinking it might take to go to Mars, there's a very high likelihood, I think it was like close to 10% of a person on that voyage not just getting cancer, but dying of cancer from exposure to not just the solar energetic particles from a coronal mass ejection, but also from the cosmic rays. So again, I think I heard correctly, you guys have a speaker in a month or two that's talking about cosmic rays that are intergalactic.
Yeah.
So energetic particles are in general bad because they impact and cause DNA damage. And then, you wind up with things like cancer and other nasties to come along. And also cause digestive upset. There's a fun story actually from the early days of the astronaut program. Many of the early astronauts were pilots, and there's this phenomenon that occurs with astronauts. And it's especially enhanced when they travel to a place like the moon, where they see these bright flashes of light in their eyes. I forget what they're called specifically, but what the leading theory on what these bright flashes of light are, they would occur like every couple minutes or so, is that they're probably cosmic rays, like intergalactic energetic protons that are being picked up by the retina. So they're actually traveling through your eye and they hit your retina and they register as a bright flash. There's actually there was like an experiment, I think, that they made this Apollo 16 and 17 astronauts wear that's like a helmet on their head to try to track cosmic rays and see if they correlate with flashes in the retina. Anyway, but so that's interesting. But in terms of effects on the body, it's definitely like sort of cancer risk type stuff. Yeah, I think that's mostly it.
Wouldn't that damage your eyes?
Over time, I imagine that it would. There are all sorts of funny medical effects that occur from being in microgravity. The flashes of light in your eyes, again, probably not really great for the DNA in your retina. I don't know how quickly cells divide in the retina because I'm not a biologist. I bet someone on this phone call is, though. But there's another effect that happens about the eyes, where if you spend a long time in space, the microgravity changes your vision somehow. And they think that it has something to do with the microgravity and the fluids and the different gelatinous pieces in your eye. I don't know the specifics of it, but I think that has something to do with it.
Does that mean, is that permanent? Does it damage the eye?
Yeah, the microgravity part, it seems to be mostly permanent.
And so your vision is no longer as good or something?
Yeah, I think so. There was this twin study that was done a few years ago with Mark and Scott Kelly, these identical twins that are both astronauts.
Oh.
And then I forget if it's Scott or Mark that spent a year aboard the space station, but that was part of the reason that he did that, is because they were trying to figure out what the medical effects were from one astronaut being in space and one being on the ground. And the vision was one of the vision changes was one of the results that came out of that study.
Is there any way to protect against them?
You can try to shield against energetic particles, but if anyone's got a good idea about how to shield against really energetic protons, call up NASA. They are totally interested in hearing about that kind of stuff. It's a really hard problem. There are some people that think that things like lava tubes on the moon are a good idea. Maybe, maybe not. I heard one really crazy idea once. Someone said they wanted to float a giant ferromagnetic piece of metal between the Earth and Mars at the Earth Lagrangian point, between Mars and the sun at the Mars Sun Lagrangian point, the L1 point. which is this region of stable gravity where you can have things orbit around essentially nothing. It's kind of cool. But they wanted to put this giant magnet essentially in front of Mars as to act as like a shield to protect against solar energetic particles, but that doesn't really do anything for the cosmic rays because they just come in from all directions all the time and you can't do much about them. We really are quite fortunate to have our life evolved on a planet where we have such a strong magnetic field. In fact, there are theories about life evolution in our magnetosphere, but again, not being a biologist, I shouldn't step where I'm not an expert.
Huh.
I see a question from Lou. Hand up for Lou.
I'm excited.
What happens when the Earth's magnetic field reverses? There must be a time for the whole planet when there's no protection.
Yeah, it's going to be fun in like a couple thousand years. I think the theory is that it probably does something similar to what we see on the sun, and that it doesn't just completely go away. You know, like we still have some residual magnetic fields. But yeah, during that time, there will be more cosmic rays that make it down to Earth. There'll definitely be aurora at all latitudes. That sounds kind of exciting to me personally. I don't know if it's worth the cancer risk, but you know, it sounds like it'll be interesting to see aurora in Florida, for example. Yeah, so when I know a little bit about this, so I can talk about it some. Yeah, so whenever the Earth's magnetic field flips, there's actually a tracker. Did you know this? You guys probably know this because you use maybe compasses and stuff to figure out where's north for setting up telescopes. So yeah, like the magnetic north is like changing and it's actually accelerating. Like the rate of change is going faster as time goes on. So yeah, a couple thousand years for sure. It'll be interesting. I mean, it is what you expect. I don't know. It's happened a bunch before, so things will probably be fine. But in terms of like electrical society, I think it might require some thought. But you know, on a cosmic time scale, 1,000 years seems really close. But you know, for a lifetime, it's really far off. So I think there's probably time to prepare.
Well, if this happened, do you think it happened 2,000 years ago?
Oh, we can actually tell by looking at magnetic surveys of the Mid-Atlantic Ridge, which is like this, section of tectonic plates that are spreading apart. You can drag like a magnetometer across the seafloor and you can see there's like frozen in magnetic field that switches directions every, 20 to 30,000 years, I think. So yeah, it happens relatively frequently if you think about it on an Earth timeline, considering the Earth's like a little less than 4 billion years old. It's pretty impressively quick. It's like flipping back and forth if you were thousands of years old, you know.
Would that have left any permanent trace that we could look for? Yeah,
so we actually do see it on the rock on the bottom of the Atlantic.
So
that's how we know that.
Would that have had any effect on animals or people?
Almost certainly.
Yeah.
Yeah, what kind of effect?
It's a great question. I'm not sure what life evolved from that would be like. But we're here, so it's probably okay.
It's getting late and the questions are slowing down. So I want to say thank you very much for your presentation, Dr. Phyllis. And you told me not to call you doctor.
It's fine. I'm used to it.
And
I
thanks
never get
everyone
doctored
for
at work,
coming.
so it's a bit of a thrill.
Yeah.
And I'll hand it over to Linda for final words.
Oh, I just thank you too. I thank you very, very much. We've learned a lot. It's been so interesting. And I knew that we could probably have you here for 2 hours. I knew that in advance.
Yeah, thank you guys so much. This has been such a delight. I've really enjoyed the questions in particular. Have been really excellent.
Yeah, I'm sure everyone's enjoyed very, very much hearing from you tonight. Thank you. And so we'll have to have you back after Escapade has had its time to do some research. And so it's launched in 2024, right? 2024 is when Escapade goes?
Allegedly. We're still looking for a rocket. It's going to be interesting because they're planning to have us as a ride share. So we'll wind up riding like backseat to some other mission. But we'll put it up on the usual places, social media. The UC Berkeley Space Sciences Lab will certainly post about it whenever we get our launch vehicle.
Yeah.
So,
well, we'll have you back
thank you
for the information.
We appreciate it.
Thank you. Good night.
All right. Take care.
Good night.
Good night, everyone. Thank you.
Thank you.